Engineering Science, Mr. Young here, just looking at the next part after balancing beams here. We've got balancing forces on beams. We've got beam reactions, so we're looking at forces, how they act vertically, and the reaction forces acting in the opposite direction from that. So similar outcomes here, using moments to solve forces acting on the beam. So again, you need to know what force is measured in, know how to calculate moments, which we'll cover just in a minute. And again, using the sum of, so that the sum of the clockwise moments are equal to the sum of the anti-clockwise moments. As you'll see in a moment, as you will see that we considered the beam to be balanced before we do any calculations, but don't worry about this the first few minutes, or if you're a wee bit confused about everything being imbalanced. Balance, it's just because we just want to make sure that the beam is perfectly sort of still and stable before we do any calculations. So similar, like I say, similar outcomes for the success criteria here, but it still links into the previous lesson where you were calculating out simple forces on beams. This is a wee bit more involving, but bear with it and see if you can do the work. Okay, and you can see the next bit now. So here we are looking at some beam reactions here. Just got a simple example, just looking at a simple beam. It's supported at either end here at point A and B, and there's two forces acting down the way. There's a 10 kilonewton force acting down here, and a 12 kilonewton force acting here. And what we want to find is the reaction forces at A and B. So R is just going to equal reaction here. So when I say RA, that's the reaction force at A and reaction force at B. Because if you think about Newton's third law, every reaction has an equal and opposite reaction. So if we've got forces acting down the way vertically, we're going to have forces, opposing forces acting up the way to keep this beam balanced or in equilibrium. Okay, if there's more force pushing down than there is pushing up, that means we're in trouble because the bridge or the beam in this case has a tendency to collapse, and that's when you'll see major disasters on the news, etc., where things have collapsed because these reaction forces going up the way to counteract these ones, they're not strong enough, or the bridge is weakened and it collapses. So to begin with, what we're going to look at is, this is obviously a beam that's sitting horizontal. So we're going to state a couple of things here, but don't worry about this first bit. This whole first bit here is just to say that the beam is balanced. Right, the beam is balanced here. That's all we're looking at. So if I was looking at this and there was these 2 kilonewton forces weren't here, but there was one point in here, the beam would have a tendency to maybe be pushed or pulled in a clockwise direction. Right, so what we're going to say, the total sum, or the sum of the clockwise moments, is equal, and the same here, if these were covered up and there was a force here, this beam would have a tendency to go in the anti-clockwise direction, so is equal to the sum of the anti-clockwise moments. So all we're saying is that it's balanced, that the horizontal forces going clockwise and anti-clockwise have balanced each other out. You can say the same with the other ones as well. You can say the sum of the moments, the sum of the forces vertically is equal to 0 just now, because they're being balanced out by these reaction forces we're going to find out. Okay, and the sum of the moments, sum of the forces and horizontal is equal to 0. Okay, which we've just said anyway above there. So all that preamble is just meaning that the beam's balanced, it's not moving or it's not collapsing. Okay, so don't worry if you're like, well, what does all that mean? It just means it's the thing's balanced, and that's all we're trying to sort of establish first of all. So if I write in here RA and RB, okay, it's just our reaction forces that we're looking for. The beam is 5 meters long. So what we're going to do is we're going to take moments. Usually you'll be asked, it'll be stated in the question, take moments about RA to find RB. Okay, so what we're saying is we're going to go, remember a moment is just, my pen holds up here, force times distance. Okay, force is measured in newtons, distance is measured in meters. So a moment is measured in both of these Newton meters, or in this case kilonewton meters, because we're in kilonewtons a wee bit here. a wee bit, we are. So that's what a moment is. So all we're doing is force times distance. Okay, so we're going to take this 10 kilonewton force and go back to RA, because it says take moments about RA, so we're going back here. So that's all I'm doing, is I'm taking force times distance back to RA that I've been asked to do. Okay, and the same with this 12 one. So to begin with, let's have a look. So 10 times 2, these are both in kilonewtons, so I could do 10,000 times 2 plus the 12,000 times whatever when we get to here. But since they're both in kilonewtons, I'm just going to keep it simple, and we'll find that the resultant force acting up the way at RB here is in kilonewtons. So 10 times 2, because it's force times this distance back to RA that we've been asked to find. These are both acting down the way, so they're both acting together, plus 12, this is this one, times the total distance now back to here. It's not times 1 though, it's times 3, because it's 2 plus 1 times 3 is equal to RB times the total distance of the beam, because the RB is here and it's acting along the total, it's going to be against the total distance of this beam here, so RB times 5 there to begin with. Okay, so we want to find this reaction force here. So we can do a bit of simple maths here, through brackets in here, because we're working these out separately. So what we'll do, times 2 is 20 obviously, plus 12 times 3, 36. It's equal to 5 RB. Now I'll swap this over here, because what we're looking for is RB here. Reaction force at B is equal to, we'll add this together, so 20 plus 36 is 56. Right? Now what I'm going to do, the 5 would be here. Now the 5 again is just this distance. That's what the 5's come from. I've just put it in front this time, but still 5 times RB. So if the 5 was here times RB, if I wanted to find out the resultant force, I wanted to bring this over, and I'm going to divide this here, okay, to find the resultant force. Now what we've got here, this point is, this is 56 kilonewton meters, and this is 5 meters. So when we divide this by this, we're going to cancel out the meters here, and that will leave us with a force in kilonewtons. So just be over 10 or something. So you'll find the force is 11.2 kilonewtons. So RB is equal to 11.2 kilonewtons acting back up the way. Okay, so that's what we found out. So that's simple as that, taking force times distance, and dividing it by the other side against the total distance here, for these simple to begin with ones here. Okay, so we found that out. So we can easily find RA now by doing the opposite. We can take force times distance back this way and do the whole thing again. It's very convoluted, it'll take you another 5-10 minutes or so to do that. However, the easy way is to, well, we're going to state here that since this is balanced, that the total amount of force acting down the way is equal to the force acting up the way. So RB and RA added together will equal these two forces acting down. So we know that the forces acting down are 22 kilonewtons in total. So what we're going to state here now is that the total number of forces acting down the way is equal to the total number of forces acting up. Alright, so total forces acting down is 22 kilonewtons is equal to RA plus RB, which is 11.2 kilonewtons. Okay, so what you'll find is you can easily just find RA now is equal to 22 minus 11.2, and this will give us a total answer. This will give us a total answer of 10.8 kilonewtons. Mental maths at its best. Okay, so we found RB by doing force times distance back to the reaction force point at A here. Worked that out, divided the total distance by the forces that we found, the total moments we found out, to find RB. And then we took the fact that the total forces acting down equal the total forces acting up, so the beam's balanced in equilibrium. And then all we did is we added the total forces acting down and took it away from the one that we knew about. which was 11.2 that we found out here. And that left us with 10.8. So that is ends up being our two reaction forces. Okay, so that's how you do beam reactions. Now, this might be quite tricky because it's probably one of the most sort of trickiest topics in engineering science at National 5. So if you find this tricky, don't worry. It's not meant to be easy, but it's used by engineers, civil engineers, structural engineers, to figure out whether or not the thing that they're making, the beam, the bridge, the structure that they're making is going to actually be able to hold and be able to take the forces that they're stating that they could. Now, it's a main part of civil engineering and structural engineering, so that's where that kind of links into. So if you do find it tricky, don't worry, it's just about practice. It's about doing lots of these so that you can actually practice them. Alright, so stay safe, have a go, see how you get on. Bye.